Ah, welcome, fine physics folk. Here we are at the start of another week, and we, I think, are going to be done with Newton's laws at this point. Um, I feel like obviously, there's always more to learn about them, but I feel like you have a decent enough understanding of the three laws, provided that you at some point download or watch on YouTube for free. All the cool scenes are there, the movie Gravity. I think that would really be a great way to kind of put together Newton's laws and be like, hey, that could happen, or that's just wrong. I mean, that's the real point of taking physics, to be able to look at movies and be like, nope, not gonna happen like that. I want to make sure, before we all part ways for the year, that you understand one of the most important and pivotal concepts, not just in physics, but in all science. That concept is energy. But before we get to energy, there are two key words that are the title of this slide that I really want us to address: work and power. They are words that are constantly thrown around, and the definition is not often well understood. Here we have a photo of the Olympic weightlifter. His name escapes me at the moment, but he is currently, in that exact moment, holding that weight still. If he's holding that weight still, is he doing work? Is he doing power? Does he have energy? What forces are happening? We're going to really kind of examine a situation like this and try to understand how these physics words will play into a real life situation. Today, we're going to start with work. Work is very simply defined. Work is a force exerted over a distance. All right, now we can all write that down. We can learn that, but what does that really mean? A force exerted over a distance. Here's what work is in a very simplistic term. Work is when you push something and it moves. Work is when you push something or it changes its motion. Okay, so what are the two differences there? So let's just say you're sitting at your desk or your bed, and I don't know, you see your pen just sitting there. If you push it and it moves, you're giving it force, but you're also doing work on it because it moves. In order to have work, you must have movement or a change in movement. Now, what do you mean when you say change in movement? So let's just say someone threw a basketball at you. If you caught the basketball, you changed the motion. Therefore, you did work. Okay? So work is force over a distance. Now, force exerted over a distance. Let's not worry about changing motion. Let's just think about it for simplicity as work is causing something to move. If nothing moves, you don't do work. Now, here's where people get tripped up. If you push the wall, and assuming it's a good wall, it's a strong wall, it's not like a flimsy wall, no matter how hard you push that wall, the wall doesn't move. Are you doing any work to the wall? No, you're doing no work to the wall. However, if you push that wall, is it possible that you move? Yes. According to Newton's third law, if you push the wall, it pushes you back, you might move back. You do no work to the wall, but the wall does work to you. The wall is working you. So, what we have here is force over a distance. W is work. Work equals force times distance. Times distance. Okay. Work equals force times distance. All right. Again, work is only done if the object moves. If there's no motion, there's no change in motion, there's no work done. Let's just think about it for our purposes this year in our remote learning, that work is only done if an object moves. Okay? So, the unit that we're going to use for work is the joule. Now, you've probably never heard of joules before. Maybe you might have heard them in a science class before, but joule is a unit for work. Joule is a unit for energy. That's the metric unit for work and energy. Does anyone know what the non-metric unit for work and energy is? the calorie. Calories measure the work or the energy in things in the United States. Interesting little factoid here. If you ever look at a food label, it'll say, calories. Calories are essentially telling you how much work, how much energy is in the food you're about to eat. If you have more calories, you're going to have more energy. But if you travel abroad and you go to Europe, you go to Africa, you go to South America, you go to Asia, you go to any other country in the world, and you look at that label, it's not going to say calories. It's going to say kilojoules. It's going to say kJ. I know you don't believe me. I know you think I'm full of it. I think you should Google it right now. See what rappers in Europe or South America or Asia or Africa, probably a country that speaks English. So find a country that speaks English so that you could at least read that much. But you will see the label will be in kJ. Okay, that's a little bit of a branch. If we were in school, we would get more into that. But I just want you to understand that the United States is backwards in so many ways. Okay, so let's look at this question. How much work, we're looking for work, is done when a 50 Newton force is exerted over 5 meters? I mean, this is the most basic of basic FEMA type equations. If you even want to know, you can write it as a triangle. Work equals force times distance. Huzzah! There you go. Work, force, distance. Work is joules, force is newtons, distance is meters. All this, I think, is going to be good review. So, work triangle. I said we can make a triangle of this. Work equals force times distance, WFD. This really isn't that bad, you guys. Work. Okay, so we're looking for work. I know 14 newtons is a force. 1.5 meters is a distance. Wow, triangle's terrible, but you get the idea. Multiply work equals 21J. Bozzuto, is it really going to be this easy? It is. That's kind of why I'm going fast. We've done triangles to death, you guys. You know how this is going to work. So, it says what force? And number 2, what force? We are looking for a force. Force equals work. Work is going to be the 28J pushed over 2 meters. Force is 28 divided by 2. Force is 14 newtons. So yes, today, the purpose of today is to kind of just make sure you are familiar with plugging into these equations. Obviously, things are going to get a little bit more complicated, but let's start simple. Question 3, how far? How far is distance? Okay, we know this. We've done this. When it says how far, that's distance. 36 Newton desk. Newtons is a force, so that's going to go right here. If 108 joules are exerted on it, bam, divide. Distance equals 3 meters. All right, simple. Just pay attention to the units. Nothing more to see here. Power. Now, power is how fast you do work. Power is how fast work is done. So you may notice that if you walk up a flight of stairs, or if you run up a flight of stairs, you're doing the same work. You're exerting the same force over the same distance, the force to move your body that distance. But the difference is the amount of time that it takes to do that. So while you do the same work in each instance to go up the flight of stairs, if you run, you use more power. And evidence for the fact that you're exerting more power is you might be a little winded if you run up a flight of stairs. Whereas if you walk, you might feel just fine. Doing the same work, lifting the same weight, which is your mass, which is your mass pulled by gravity, which is your weight, the same distance. In fact, going back to the original picture, the weightlifter is really a great example of this. If you lift weights, well, I mean, okay, so I could get into this. You don't want to lift weights so fast that you get into a rhythmic motion, and then what happens is the momentum of the weight change actually takes some of the energy out of your lift. You don't want to do that. So like you may see people who go so fast, what they're doing is they're actually just creating a rhythmic wave momentum, and it's actually helping them move the weight faster. They're not working their muscles as much. So when you do weightlifting in the gym, what you want to do is you want to do controlled lifts, but you want to do it quickly. You don't want to like lift one, do one rep, get up, walk around the gym, get some water, go back down, do a second rep, because there's going to be so much time between that. Your muscles are going to heal. You're not going to use enough power to really get the weightlifting benefit that you want. Okay, sorry, going off tangents. Guys, there's so much I want to explain about this to you, but it's just going to be tough right now. Work equals power times time. So power is measured in watts. Okay, so we're going to slow down a little bit. I want to really kind of get to some of the good stuff here. Power is measured in watts. Work, power, time. All right, here is the new triangle. So we had the WFD on the other page, and now we have the WPT, work, power, time. Interesting. What we're going to recognize is that power and time are inversely proportional. Power and time are inversely proportional. Let's see about that. So based off this triangle, power equals work divided by time. Oh, if I'm doing the same work, lifting the same weight, if it takes more time, it's going to have less power. Okay, an inversely proportional relationship. Nice. I get that. That makes sense. So let's think about it in terms of physics. Power is measured in watts. Now, if you've ever seen the unit watts, it's probably been on a light bulb that you've changed somewhere in your house. 60 watt, 75 watt, whatever bulb that you may have. But that's probably the most common place you've seen watts. And watts relates to electricity. Wait a minute. Are you saying that doing work and energy can relate to electricity? Well, what I'm saying is that all these are forms of electricity. And if you've ever been to the Science Museum where you're like spinning a crank or riding a bike, and the faster that you ride the bike, the brighter the light bulb gets, what you're seeing in situations like that is as you do more power, as you do the work in less time, you are creating more power. And then with more power, the bulb gets brighter. So the very last thing that we're going to touch upon in this class is electricity. We're going to kind of connect this power to all the electricity stuff. But before we get there, I know I'm jumping all over the place. There's things I want to get into. What I want you to know for today is that work is when you push something and it moves, and power is how fast you do that work. If you get that, then you're good. So how much power is produced when 60 joules of work is produced in 3 seconds? Okay, simple. Triangle time, bam, I already wrote it up there. It's really simple. Work is joules, time is seconds, power is watts, and here we go. So now we have a power triangle. So we actually have 2 triangles that we're working with. We have the WFD and the WPT. I'm going to go a little bit slower on this triangle because there's some things here that students will mess up. All right, number 1 says how much work. So we're looking for work. We're looking for W in the triangle, okay? This is one thing that students will mess up. When it says there's a 120 watt bulb, that's the power. When I see W as a unit, as a watt, I know that that's representing power. When I'm talking about equations and I see W, like in the triangle, that W means work. So the W, depending on how you see it, will either mean work or watt. It'll either mean work or power. So this is where context is going to be important. When you see W as a unit, it is power. So how much work? This is really simple now. The work is going to be 360 joules. Awesome. How much power? Okay, so now we're looking for power. So this one's going to be easy. So we're looking for power. Oh, 1,200 joules, that's work. I know joules is work. And 4 seconds. Okay, this is easy. Bang. P equals 300 watts. Okay. And then how long? How long is time? We'll take to get 60W. 60W. When I read it in a question, that W stands for watts. Those watts are power. So the 60 actually goes down here. Even though it says W, and your gut is going to be like, well, that's the W of the triangle. No. When you read a question, the W is watts. 30 joules goes up here. So T equals 0.5 seconds. All right, Pizzuto, that was confusing. I'm going to be honest with you. I don't get it. Huzzah. This is why I made the slide. I understand that this is going to be tricky. So we need to keep units straight. So for those of you who are taking notes, this needs to be written in your notes. For those of you who just like watching the video and hearing my voice again and again, this is the slide that you're going to want to pause on while we do the work for tonight. So we have broken this down into both quantity and unit. So when you see units, these are the labels after a number in a question. Labels after a number. So if I see something like 45N, that's going to be 45 newtons. However, when I look at quantities, these are going to be the symbols in equation. Symbols in equations. So essentially the symbols in the triangles. So when we have the triangles, we have the WFD, and we have the WPT. Because these are equations, this W stands for work. The unit for work is joule. Conversely, if you read a problem and said, I have 45 joules, you know that joules are the unit for work. Their work and joules are connected. So when you see the W in the triangle in the equation, it's a quantity. It means work. Okay, W's, when they're in the triangles, they mean work. So force is measured in newtons. We know that. Distance is measured in meters. We know that. Power is measured in watts. So when I see the capital P in the equation, that stands for power. So we would say that the power equals so many watts. So actually, this is actually really important. We would say power equals 45 watts. That's what this is saying. Power equals 45 watts. If I would write this, work equals 45 joules. You see that these labels here are, because they come after a number, they mean these words. Because these don't have a label, that means they mean these. All right? And then time is, of course, measured in seconds. Simple. We got this. Don't get tripped up. Okay, I want to get back into the weightlifting example one more time. I said that work is done only if you move an object. So if you have a weightlifter holding a massive weight over his head, can't do that forever. Your arms get too tired. But in the moment, in the instant where he's holding it still above his head, is he doing any work? No. Because it's not moving, in that moment, he's not doing work. That doesn't mean he's not exerting force. That doesn't mean his arms are at rest, like are resting and they're not doing anything. But he's not doing work in that moment. Only when the barbell is going up or coming down is work being done. When it is still, it is not doing work. Work requires motion. Okay. So little Susie and Nellie Newton each have identical masses. If little Susie walks up a flight of stairs and Nellie Newton runs up a flight of stairs, well, who did more work? They have the same mass, and they went the same distance, the same flight of stairs. So they did the same amount of work. They went the same distance. But who did more power? Because Nellie Newton went up the stairs in less time, because she ran, he did more power. Less time means more power. So if you do something quicker, you use more power. Doing something quickly doesn't affect the work. Okay? Think about it as running a race. If you run 100 meters, you go 100 meters. That's the distance you go. It's not like whether it takes you 30 seconds or 10 seconds to go 100 meters. You're not going a greater distance. The only thing that's different is you're going the same distance, but the only difference is the time. And is it easier to go 100 meters in 10 seconds or 30 seconds? It's easier to go 30 seconds because it's less power. So, just quick recap. Work is force over distance. Work is movement. If you do not have movement, you do not have work. That's it. That's the essence. If you push something and it moves, you got work. Power is how fast it's done. That work is done. So you could spend all day to lift a pen from the floor to the ceiling. You do the same work as if you just lift it in a moment. But the difference is the power. So again, lifting the same weight, the same distance does the same work. However, lifting it faster uses more power, even though the work is the same. So when you go weightlifting, you go to the gym. Every time you lift the weight a distance, you're doing the same work. But the difference is the power that you exert. Okay, this is the good stuff. The double triangle. So, we have two triangles. We have the WFD and we have the WPT. Let's just see how this is going to work. Number one says, how long? Okay, how long? How long? Oh, how long is time? How long is not distance? Distance is how far. So we're looking for time. We push an 18 Newton chair. All right, 18 newtons. Thankfully, I wrote those notes down. I know that newtons is a force. 4 meters. 4 meters. 4 meters is a distance. I hope we know that meters is distance at this point of the year. And then 10W. Okay. Because it's 10 followed by a W. I know that W is watts, and that is the power. So this is what we're going to do. We're going to plug it into the triangles. We're going to plug in what we can. I don't know the work. I know that the force is 18. I know the distance is 4. I'm looking for the time, and I know that the power is 10. So this is how it's going to work. If I can get the work in one triangle, I can get the work in the other triangle. So if I look in the left triangle, I have the 18, the 4. If I multiply them together, that's going to equal 72 joules. If I know that this is 72 joules, I know that this is 72 joules. 72 divided by 10, the time is going to equal 7.2 seconds. That's why I'm calling this the double triangle. You're going to write out both triangles, fill in what you can, solve for the work in the first triangle. The work in the first triangle is going to be the work in the second triangle, and then you divide it out to solve for whatever you're looking for. Bizzuto, I didn't follow that. Let's do another. Agreed. How far? Stop. What are you looking for? Looking for a distance. Okay, good. 30 Newton. Okay, 30 newtons. 30 newtons is a force. I cannot stress how important it is to make this list. If it is lifted with 20W, 20W, okay, 20W. Okay, because it's W, is it watt or work? Well, because this W is after a number, I know it's watt. It is the unit. It is the unit for power. For 3 seconds. And that's a time. Okay, let's see what we got here. I got the WFD. And I got the WPT. Okay. Nice. All right, so let's fill in what we know. We know the force is 30. Okay. Don't know the distance. Distance is question mark. But I do know that the power is 20, and I know the time is 3. Oh, interesting. Look at that. Look at how easy this is when I have these labels here. I'm going to tell you, if you try to do this too quickly, because these units are so similar, you will make mistakes. You need to make this list on a scrap piece of paper as you do the work today. 20 times 3 is 60. If it's 60 here, it's 60 here. Hey, it's kind of like the Newton's third law thing we just did. And then D equals 2 meters. There is a connection with all this. So you know you're moving a distance of 2 meters. How much power? Okay. P equals question mark. P is power. To move 12 newtons. 12 newtons is a force. 4 meters is a distance. And I'm pretty sure that we know that 20 seconds is a time. And if we don't, well then, dang. Okay, so we got WFD. The reason I want to do all these problems is because I want to make sure that you can kind of follow along and that you feel comfortable setting this up yourself when we do the problems for homework tonight. I know one of the problems of the distance learning is people are saying I'm not doing enough practice problems, so I want to make sure I get more practice problems done in the presentations. Okay, let's plug in 12 newtons, 4 meters. Okay, the power is what we're looking for. The time is 20. Oh, okay, look at this. 12 times 4 is 48. Nice. 48 here, easy. 48 divided by 20 is 2.4. The power is 2.4 watts. Oh, Bazooda, there's gonna be decimals in this. Yes, I love decimals. And the very last one, I almost feel like I don't need to go through it fully. I'm really going to talk through this as fast as I possibly can. The distance is 5 meters, 100 watts. See, look at that. Now I go fast and I make mistakes. Come on, Bazooda, get your head in the game. 100 watts is power, and then time is 10 seconds. Awesome. So we're going to get the WFD, and then the WPT. Love it. So the force is what we're looking for. The distance is 5. Wow, my handwriting has gotten terrible. I mean, like, I feel like I'm in the classroom again. And then this is going to be 100 times 10 is the work here. The work here is going to be 1,000. 1,000 divided by 5. The force is 200 newtons. Look at that. Easy. Today's work is going to be a little bit different. I am going to have you do it in terms of a Google form, like a quiz on a Google form, and you will literally just do a multiple choice of select the right answer and turn it in, and then it will grade it for you right then and there. Because it's going to grade it for you right then and there, that's the grade that's going to go in Power School. So take your time. Make sure you feel comfortable with what you're doing. Look back. Because of that, I gave you plenty of practice problems to look at. Look back at the practice problems. Ask questions if you have it. And we will be good. And this will be good. Thank you guys for this. We are just getting ready for the good stuff. Energy is coming next time. I will see you guys then.